Okay, so I'm catching you guys up, videotaping, because I forgot to videotape, so I'm catching you up. So we started with yesterday, we went over filtration and distillation. And so what we're doing today is we started talking about solubility, which is the amount of the substance that will dissolve in a given amount of water at a certain temperature. And this is important because if you increase the temperature, the particles in the solvent will move farther apart and you will be able to increase the amount of solid in the solvent. But we're going to talk a lot more about that in a minute. So we talked about nature tending toward lowering the potential energy. And what I did was I showed this graph, which looks like this. And we had this graph in class, and it looked like this, right? And this was potential energy here, and then down at the bottom was bond energy. And the question is, where is the point? Oh, this was bond length. Sorry, it's bond length. Sorry. Okay, bond length. And the question was, at what length would the bond energy be the greatest? And so we said, oh, it's going to be right here, whatever bond length that that's going to be the bond length where the greatest energy is. And the reason is because the potential energy would be least at this point. And so as the potential energy decreases, the bond energy increases. And so the example that I gave was a proton and electron attracting each other. The potential energy is decreasing as they move toward each other, and the energy within that attraction is increasing, but the potential energy is decreasing. Next, we talked about solutions tend toward mixing, which raises entropy. And entropy is represented as delta S. And there's a tendency of the universe or the surroundings to spread the particles or move toward what we call increasing chaos, move toward greater energy dispersal, right? In increasing delta S, increasing chaos. And so actually, which I didn't say before, you guys, is that when you put a substance into a solution and it dissolves, it actually, if you were to say put salt into water, part of the reason that it does dissolve is because when it does dissolve, it increases the chaos. Those particles will spread, and when they spread, that increases the delta S. So the delta S is positive because it's going from this tight molecule into those particles moving all over the place. So that actually is an increase in delta S, and we're going to talk about that. But not all particles will tend toward that because they might simply mix and they might not actually interact. And so the example is if you take two inert gases, they aren't actually going to dissolve, and so they might just sit next to each other, in which case they're not going to do anything other than just sit next to each other, and so their delta S might not actually change. Or you could take something like two actual substances like oil and water, which will not increase the delta S because they won't mix at all. They have no interaction at all. So if solutions will want to mix, that would raise the entropy, and that's positive. So if they have that ability, they will do it because it will increase the entropy. Next, we talked about the intermolecular forces between the solvent and the solute, the solvent and the solvent, and the solute and the solute. So here are the examples: water and salt, water and water, and salt and salt. So here is salt and salt, and I showed you that like they line up, and because it's an electrostatic force, they're all connected together, right? They're all connected together. They're formula units, all connected together. And as the water goes by, the positive hydrogen connects to that chlorine, and this intermolecular bond is stronger than the electrostatic force between the sodium and the chlorine, and so it peels that chlorine off. And by doing that, it actually creates that solvent-solute bond. And if that is stronger than the solute-solute bond, then the solute will dissolve in the solvent if that bond is stronger. Also, we have a solvent here and solvent bond, which is the hydrogen bond between the two. That has to be weak enough that it breaks off and that it will help to create the solute-solvent bond. And then up here, we also have to have that actual solute-solvent bond to create. So there's 3 different types of bonds that have to be available and to be able to be created. Next, which is where we are right now, we're talking about like dissolves like, which is that polar solutions will only dissolve in polar solutions. It's never okay to use like dissolve likes as a reason, an explanation on the AP exam. I use that as an opening sentence, and then I explain it by saying polar substances will dissolve polar substances, and then you can say non-polar substances will dissolve non-polar substances. But the idea is that if you're going to say either one of those, there's no reason to say like dissolves like. Hydrogen bonds will help any substance dissolve in water because water has hydrogen bonds. You can see that up here. See the hydrogen and the oxygen? This is a hydrogen bond right here, the hydrogen and the oxygen. So this hydrogen bond with the hydrogen from one and the oxygen from the other, it's a pretty strong bond. It's a pretty strong intermolecular bond. So any hydrogen bond will help dissolve a substance in water because it's pretty polar. But lack of polar bonds will cause a lack of dissolving, for example, oil in water. So next we talked about hexane and determining if each is soluble in hexane. So we talked about the definition of ane being a single bond, and ene being double bonds, and ine being triple bonds. And we decided that we would put those on the next test. So you're going to want to know those definitions. Ene, ane, and ine. And we'll also put hex on the next test too. So we'll put those Greek prefixes on the next test. Mono, di, tri, tetra, all of those Greek prefixes. We'll put those on the next test too, all right? Somehow. I'll figure it out and I'll let you know how. But those will go on the next test too. Because this is a pretty short unit. So let's shove some stuff on it. All right, so we drew out hexane, see 6 carbons, hex, and then they all have single bonds between them. So that's the ane part, all right? Okay, now, would water be soluble in hexane? What do we think? No, it would not, because what we decided was that hexane was non-polar. There are no polar ends to it. It's symmetrical, so that's the first thing. And there's no polar ends, so there's no hydroxides or chlorides hanging off there. So it's non-polar. But water has the oxygen and the hydrogen make polar ends, right? So that's definitely not going to be soluble. Or rather, hexane will not be soluble in water. What about ammonia? Oh, no. Yes, ammonia will. So let's draw ammonia. So if we draw ammonia, does that change your mind? Does that look polar? Yeah, that's definitely polar. Okay, so I did see somebody go, oh, okay. So that's definitely polar. We're looking at this, this lone pair up here creates a very polar molecule, by the way, okay? It's extremely polar. And it goes this way, and then it actually goes this way, so it's going to create a dipole this way. Also, hydrogen bonds. Anytime that hydrogens are attached to, here they are again, to these, FON, whoop, okay? You've got hydrogen bonds. Oh, sorry, I was thinking about water. Thank you. Okay, so Natalie and Gino were like, no, hexane is nonpolar. So there we go. No. No. Sorry. I was thinking that it was water. Sorry. Okay. So it is soluble in water because of the hydrogen bonds, not soluble in hexane. That's a no. Thank you. Okay, next. Propane, this is by the way, the formula for the propane that you use in your propane tank, right? And notice how small it is. It's pretty small, right? It's a small molecule, 3 carbons, which is why it's a gas at room temperature. Butane is actually sort of the line. Pentane is more liquid, like easy to turn to liquid. So like at like 60 degrees, 50 degrees, pentane is liquid. Butane is sort of the line. It under any kind of pressure at room temperature, it goes into liquid, right? So you have to keep the pressure in butane. In those lighters, you have to keep the pressure really open, which is part of the reason that in those lighters you spin the wheel and there's something in there that opens up the pressure, right? But if they're under pressure, they turn to liquid. But propane is always gas, all right? That's why you can put lots of propane into those tanks and you can compress it down so they're very heavy when they're full, because you can't compress a liquid, right? But you can compress gas. So you can compress that propane into that little tank. All right, propane, yes or no? Yes, it will be a dissolved gas in hexane, which is a liquid, because it's large enough. Look how big it is, right? Comparatively, okay? Remember, these are going to be temporary dipoles, London dispersion forces, but this London dispersion force is large enough that it will be a liquid. All right? Hydrogen chloride. No, good. Okay, now, miscible means that substances are soluble in each other in all proportions. Weak solvent-solute interactions will be overcome by stronger solvent-solvent interactions. So these are weak, solvent, strong, solvent, solvent. So this was a very interesting chart. So I typed the whole thing in for you because I wanted to talk about it, all right? So look at the small, see, meth, eth, probutanol, and pentanol. All right? So actually, these are the ones that you should study, not the mono, all right? Meth, eth, and prop, and but. All right, now, we'll talk more about it tomorrow. So look at how small the methanol is, and then the ethanol, and then look here, miscible with water. Because this is polar, ethanol is polar, propanol is polar, because it's so small that alcohol does affect the polarity. See that? But then you get up to butanol, and it's the exact same thing, but those 4 carbons, that one alcohol, that one hydroxide, doesn't affect the polarity enough to make it mixable, right? Mixable, right? It doesn't make it soluble anymore, because those 4 carbons are enough to cause it not to be soluble. Does that make sense? Just the 4 carbons are enough. And then, of course, pentanol, nope, too big. Remember, now we're into London dispersion forces and hydrogen bonds. So on a test, what kind of bond of intermolecular forces are in butanol? London dispersion forces and hydrogen bonds. It is not soluble in water. Why? Because the London dispersion forces are large enough and the hydrogen bonds are not large enough to overtake it. That's why. Where's the line? 4. Why? Well, up here, propane is large enough because it's liquid. It's a gas. Where's the line? Butanol. Butane and butanol, that's the line, those 4 carbons. We get to 5 carbons, it's not. And pentane, by the way, is a liquid. Okay? Next, we look over in hexane. First 3, not soluble. The 4th one is soluble. Why? Those 4 carbons are enough to override those hydrogen bonds. Are they still there? Yes, they are. They are still there. But they do not override the London dispersion forces. Okay? They're not strong enough to hold the whole thing together. Does that make sense? No? Yes? No? Yes? No? Yes? All right? So again, your notes. Why does this happen? Keeping this in mind. Okay, where's the line? This is all about intermolecular forces, right? All right, so the 4-carbon chain is bigger than the hydrogen bonds. So the London dispersion forces override the hydrogen forces, okay? All right. Right, so I think we're going to stop here. Now I'm going to post, when you have a few minutes if you want, I'm going to post the homework on Canvas. So I'm pretty sure, I just didn't know how far I would get, so I'm going to look it up and I'll post, it's going to be in the textbook and I'll post it on Canvas, okay?